Okay, hello everyone. I welcome you all to day two on programming with Sycl. And today we will see what is devices, what is device and device selector. We'll see about queue, uh, the Sycl code structure. We will talk about buffers, accessors, and the dependency between them. We will see the synchronization issue, and then finally, if we will get some time, we will see matrix multiplication and how we can sort numbers and SQL. Okay, so let's start. So, what is device in SQL? So, device basically represents the specific hardware platform, such as GPU or CPU. Uh, so, in SQL, what happens is that, or in any parallel programming language, we call device as uh, GPU and host as CPU. Okay, so basically, device is telling us that the specific hardware that we select for the SQL kernels to get executed. Okay, now coming on to what is kernel, the keyword that we have seen in the previous definition of device. So, what is kernel? Kernels are the parallel functions that perform computation on the data running on the device, such as CPU or GPU. So, these are basically parallel line of codes that we write for the off computation on the device like GPU. And what is device selector? So, the device selector class enables us uh, to select the particular device that we want. Okay. Now, moving on to the next slide. So, what is queue in SQL? So, in SQL, every work is submitted via commands to a queue. Basically, we can say that uh, queue queue is associated. Queue has an associated device that any commands enqueued to it will target, and there are several different ways to construct a queue. The most straightforward is to construct a default one, which will let the runtime, SQL runtime, choose a device for you. Okay, so all in all, basically a queue in SQL is like a to-do list for a computer's processing unit. It's a place where you can submit tasks to be executed on a specific device like CPU or CPU. So keep in mind that a queue can map to one device, but multiple queues can map to the same device. Here is how we can make a queue. Okay, this is the keyword. Okay, queue. Here you can write anything. Instead of queue, you can write your name also. Okay, so this is the name of the queue. Here I have just written capital Q, and this is GPU selector V. So this is the syntax basically. Yes, this is how we write queue.submit when you want to submit any work to the device via queue. Okay. Now, uh, what we just saw in the previous slide that one queue can be associated with only one device. Here, queue A is associated with GPU, and multiple queues can be related with a single device. Okay, so a single device FPGA is related to two queues. Here we can see that QB and QC. So in this uh, in today's lecture or in programming with SQL, we will not talk about this FPGA. This is a separate device. Okay, here we are talking about here we will say only about Q. Sorry, GPU. Okay, so here creating queue targeting any device. What does it mean by any device? So whatever the SQL runtime will choose for you, the default. So here, how you can create that default one. But if you want to target a pre-configured classes of device, so this is how you will write it. Q CPU selector. Uh, this will give you some errors. So this is how we write it. Okay. So this will let whatever the queue that you have made, it will associate it with the CPU. And if you write GPU, it will associate that queue with the GPU. So this is how we can select GPU, CPU is a simple code. You can just compile it. It will run. Okay. So, so this is the device selector. The device selector is letting us to select as a GPU selector. Is letting us to select is letting us to select the GPU. Okay. Similarly, CPU, default, host. Okay. And whatever we will select over here. Okay. We are naming it as just selector. So this is the keyword over here, and this you can name anything. Okay. And this selector we have written over here so that the queue will get to know that to which selector I to which device I it will get associated with. So this queue is getting associated with the selector. The selector this will be replaced by this GPU selector. Okay. Now, if you want to know the information about the device, if you want to know how much memory is allocated to that device, okay. So this is how you can get that information. Okay. So this is just a queue dot get device. So it's talking about the device that the queue is associated with. Get information. Okay, and this is the syntax for the device name and all. Let me compile this for you. So now I have opened a terminal. Sycl D2. Let's take a file cpp file named as program 2 dot cpp. Okay, here I copy paste that code, save, and then first of all I have to. Okay, let me first show you that by default. So wait a second. So by default, as you can see over here, that we have one CPU. Okay. So by default, we have one CPU and one FPGA. There are no GPUs. So if you want GPU, then you will have to request for it. Uh, Let me see the command. Okay, so this is the command to request for GPU. So now, when you will write Sycl list, ls is called list. So now you can see that now we have one GPU. Okay. Now I have to run that program2.cpp, which I have made. So ICPX F Sycl. So I am inside MTP, then Sycl A2. Inside that program2.cpp. Program2.cpp. Again Sycl A2. Program2.out. So these are a couple of warnings, not couple of. There are a lot of warnings, but yeah, there are just yeah only two warnings we are getting. So you can ignore that. It will execute. So after compiling this program 2.out, we can see that inside the MTP and then inside a Sycl D2 folder, there is one program 2. File which is executable. So now we will compile it. It has already compiled. So now we are executing that .out file. Oh. So here we can see that it is printing the device name. So if you want some more information, let me copy paste that. This will give us slightly more information about the queue. So here I am going to print device name and the max memory allocation to that device. So now I have compiled it again. Let's run the executable file. So here you can see that the selected device is Intel UHD graphics and the maximum memory allocation is this much. So now what if I will do instead of GPU, if I'll comment this line and I'll select the CPU as my device, then I've saved it. Now let's run it again. Yeah, so now selected device is Intel Core TM, something is written. This is the clock speed. So this is CPU. Okay. If you will search it, you will get to know that this is one is CPU. And as you can see over here, that the memory allocated to CPU is slightly more than the maximum memory allocated to GPU. For confirmation, let's count the number of digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, it's 11 digits. So there is that GPU. Yeah, this is the GPU. For 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is of 10 digits and this is of 11 digits. So the memory allocated to CPU is 4. Okay. Now coming back to the slides. Yeah. So here we so the code that executes on the host have full capabilities of C++ available at application and command group scope. So what does it mean is that when a code executes on the host in Sycl, host means CPU. So at that time, it has the full capabilities of C++ available. Uh, this means that you can utilize the entire range of C++ functionalities, including dynamic memory allocation using malloc or new function pointers. You can use the recursion and other advanced features of the C++ language. Okay, so the host code in Sycl typically involves tasks such as data setup, management, and coordination, as well as handling of tasks that don't need the specialized parallel processing capabilities of the device. Whereas, uh, on the other hand, the code that executes on the device, that is at the kernel scope, there are certain limitations. Okay, so what are those limitations? That you cannot perform dynamic allocation over there. You cannot use function pointers, and there are no recursion. You cannot use recursion. So why that? Because uh, some of why there are this much limitations. This basically these limitations are imposed to ensure that the kernel code can be efficiently parallelized and executed on the specialized hardware without the overhead and the complexities associated with the dynamic memory management and a certain advanced C++. Okay, now so in Sycl, there are two models for managing data. One is the buffer accessor model, and other one is the unified shared memory model. And today we will see about the buffer accessor model. And tomorrow you will see what is unified shared memory model. Okay. So in buffer accessor model, what happens is that the data management is done through the use of buffers and accessors. That's why it has named buffer accessor. So a buffer is basically container for data that resides in either the host or the device memory, and the accessors act as the interface to access and manipulate data within these buffers. Now, buffers are used to store data that needs to be shared between the host and the device, and they are created with specific data types and the sizes, and can be read or written to using accessors only. Okay. Now, accessors provide a way to specify how data will be accessed and modified by kernels executing on the device. They enable the data within the buffers to be read from or written to during the computation phase. Now, accessors also handle data movement between the host and the device automatically, ensuring data consistency and synchronization. So you don't have to explicitly copy from host to device and then device to host. Okay. So when we work with buffers and accessor model in Sycl, the programmer primarily deals with the creating and managing buffers and accessors to handle data transfer and manipulation between the host and device. And this model helps in abstracting the complexities of data movement and synchronization, which allows programmer for a more streamlined approach to develop parallel application with Sycl. So I was telling about this, the buffers and accessors. You can read smallest definition. Now, let's move on to the next slide. So here it reads, a Sycl buffer can be constructed with a pointer to host memory. So here, as we can see that suppose this is the function that we have called from the main function. Suppose there are three arrays declared in the main function. One is array A, another is array B, and another is array C. And we have also passed n, which is the memory, which is the number of elements in all these arrays. So let's suppose that all the three arrays have same number of elements, that is n. Okay. So what first line is telling us that we have created buffers for array A, B, and C using the pointers in the host memory. Okay. So this buffer corresponds to integer array A, and then this buffer corresponds to array B. Similarly, buffer C is correspond to array C. And now moving to the next line, for the lifetime of the buffer, this memory is owned by the Sycl runtime. Now, once you have made buffers for these arrays, you should use buffers only for manipulating their data, or or for rest of the time until the buffer is not destroyed, or you explicitly copy whatever changes you have made in the buffer back to the original arrays that is in the A, B, C. Till then, you should use only buffers, because whatever changes you made, it will reflect in the buffers. Okay. So what happens is that when a Sycl buffer is created, the Sycl runtime takes, we can say that Sycl buffer takes the ownership of the memory pointed by the host memory pointer. And this implies that a Sycl runtime manages the data within the buffer through its lifetime, and which ensures the proper synchronization and data integrity. Now, the third line states, when a buffer object is constructed, it will not allocate or copy to device memory at first. What does it mean? That when the buffer object is created over here, this is the buffer object. So when the buffer object is created, it does not immediately allocate or copy the data to the device memory. Okay, and this approach, why this happens? Because This minimizes unnecessary data transfer and memory overhead during the initialization phase. So when does it happen? When the memory is allocated to buffers. Okay, so this will happen only when once the Sycl runtime knows that the data needs to be accessed and where it needs to be accessed. So when we are using, so for these buffers we have made accessors because we can only manipulate the data inside the buffer using accessors. So when we have made accessors, the actual data transfer from the host memory to the device memory occurs only when the Sycl runtime determines that data needs to be accessed with the help of these accessors and identifies that the specific location where it needs to be accessed. Okay, so this is often done to optimize data movement and to ensure that data is available on the device only when it is required for computation or processing. So here it gets know that you have to perform some computation, then then only the memory will be allocated to it. Or you can say that the moment accesses are made, at that time memory will be allocated to the buffers. Okay, coming to the next slide. This is the exact code that I have written over here. Here the 3 points that I have mentioned. Kernel invocations are executed in parallel. So yeah, this is the kernel invocation which will execute in parallel. We will see later line by line what each of this statement means, handler and operation, s dot parallel for range. Just for now, just know that this is a kernel means this. Okay, kernel is invoked for each element of the range. Okay, we will talk about it later. Okay. So constructing an accessor specifies a request to access the data managed by the buffer. As we just learned that you can only change or manipulate the data of buffer with the help of accessors. And the second line reads that there are a range of different type of accessors which provide different ways to access data. Yeah, there are a couple of different type of accessors like host accessors. You can make device accessors. We'll see one of them. Now, coming on to the next slide. So here we can see that when an accessor is created for the buffer, it is associated with a command group via the handler object. Okay, the command group are basically the parallel lines of code that you have written. So whatever queue to whatever device the queue is associated with, when you made accessor, that the command group, the lines of code will get to know with the help of accessors to which device they will have to execute. That is where they will have to execute those command group lines because the accessor is related uh, to some handler and that handler is associated with the device. And we will see that in the code, so you will get to know better, you will understand better, and we see it all these things in the code. But just now, just have some patience, learn the keywords. So here it says that once the Sycl scheduler selects the command group to be executed, it must first satisfy its dependency. So what dependency I'm talking about is that when the Sycl scheduler, basically what is scheduler in operating system, there are different kind of scheduler in operating system like job scheduler, task scheduler, IO scheduler. So their task is to manage the their task is to manage the memory and devices. All. So you can like you can learn. Just Google it. What is scheduler? Okay. So what happens is that when the Sycl scheduler chooses a group of tasks to run, it needs to make sure that all the data required for this task is available and ready to be used. Okay, this might involve moving the data from the computer's memory to the specific part of the computer, that is the device, where the tasks will be done. However, if the data is already in the right place, it does not need to be moved again. Okay, let's imagine. Suppose you have some foods and materials in a storage room. Okay, here the storage room is like the computer's memory and the workbench, the device where you actually build things. So before you start working on a project, that is the command group, you need to bring all the necessary tools and the materials to the workbench. And if everything you need is already there, you don't need to move it again. And this way, you can start working right away without wasting time fetching things back and forth. So that is the thing. Now, here's a simple definition of scheduler. A scheduler is a program that manages the order and execution of tasks or process to optimize resource utilization and system efficiency. Simple definition. Now, here, it reads that data will remain in device memory after kernel finishes executing until another command group requests access in a different device or on the host. So what it tries to tell is that after a computer task called a kernel, okay, so this is the kernel. So after a computer task or a kernel finishes using some data on a specific part of the computer, okay, on a specific part of the computer that is on the device. So that data might stay there for a while, even if the task is done, and it will remain there until another task needs it on a different part of the computer or on the main part of the computer, that is the host. And the second and the second thing says that when the buffer object is destroyed, it will wait for any outstanding work that is accessing the data to complete and then copy back to the original host memory. So it means that when you are using a set of data in your program, the program waits for any ongoing work that is still using the data, that is still using that data to finish. And once all the work is done, the program copies the data back to the original space in the main part of the computer memory, that is the host, so that it can be saved properly. And this way, you make sure that nothing is lost or changed by mistake. We will also see that in one of our example in the code. Now, here is the simple code. So first of all, what we are trying to do over here is that there are two arrays, A and B, and suppose there are n elements in each of them, in A, B, and C. Both are of size n, and we're trying to add both arrays and get the result in array C of size n. And this operation is executed in parallel for each element of the specified range. So let's go word by word. So the q dot submit. Okay, so the q dot submit initiates the submission of a task to a queue. This queue represents a target execution environment such as GPU or a multi-core CPU. Now, the and handler add and edge that is written. So this is a lambda function. You can see what's the lambda function in programming in C, C++, basically C++. This is basically a lambda function that takes a reference to a handler object, which is edge. And the handler object is typically associated with a specific command queue that is used to define tasks or kernels for execution in that queue. And the AND syntax, which is written over here, this the AND syntax captures all variables by reference, making them accessible within the lambda function. And the as.parallel for inside the lambda function is used is a parallel for loop, okay, which is defined using the parallel for method of the handler object edge. That is why we can call it we can call it through edge.parallel for. So this loop will execute a function in parallel for each item in the specified range. Okay, the range one, and what does it mean? It means that the range, it basically tells us the range over which the loop will execute. In this case, it's a one-dimensional array. So ABC are one-dimensional array with a size n. The loop will iterate from 0 to n-1 simply. So if it would be a two-dimensional array, we will write 2 over here. Then we will mention the n comma m, whatever is the 2D size of the array. Suppose the n is the row and the m is the column number, then n comma m we will have to write. Now coming on to the equal to id 1 I. So this is another lambda function. Okay, it represents the operation that will be executed in parallel for in parallel for each item in the range. So it takes id1 object I. So this is object. This is the id1. So basically you can say it as a class. Therefore I is its object. So object I as parameter it is taking, which represents the current index of the iteration. So I basically representing us the index. So and the operation is simple. There is an operation that computes the value of a at index I by adding the values of b and c at index I. And this operation is performed in parallel for each element of the specified range. So I hope that is clear. Now moving on to the next slide. So this is just another way to write. Instead of id1, you can write item 1 over here. And since the array is of one dimension, so the id is of one dimension only. If the array is of 2 dimension or 3 dimension, then you will have to write 2 over here, 3 over here. Okay. Now, if you'll write item, then this is what you can use. Auto I equal to item dot get ID. Similarly, auto R equal to item dot get range. Okay, so I will give you the index number and R will give you this 1024. This is just another way to write. Now, coming on to the command group. So in the buffer accessor, sorry. So in the buffer accessor model, commands must be enqueued via command groups. What is command group? A command group represents a series of commands to be executed by a device. So these commands include invoking kernel functions on a device, copying data to and from a device, and waiting on the other commands to complete. Now, here we can see that the command groups are composed by calling the submit member function on a queue. Okay, the submit function takes a command group function, which acts as a factory for composing the command group. Then the submit function creates a handler and passes it into the command group function. And then the handler then composes the command group. Okay. So let me tell you what a handler actually does is that the handler. So let's start from the beginning. Like when you work with the Sycl, an accessor is like a tool that helps you access and work with the data in specific container known as buffer. And the handler object is like a guide that connects this tool, that is the accessor, with the right container, that is the buffer. Because buffer we declare outside the queue and accessor for that buffer is created inside the queue. Okay. Like here you can see that buffer we have created outside the queue and accessors we have created for it inside the queue. So handler will associate this accessor with the right buffer. So where we will, yeah. So the handler object is like a guide that connects this to the accessor with the right container, that is the buffer, and tells it how to interact with the data inside it. That is whether to read, write, or both. So the handler object, we can say that the handler object is important because it ensures that when your computer does the actual work on the data, work like calculation or processing. It knows exactly which data to work on and how to work on it and where to find it. So this way, everything is organized and the computer can handle the data in the way it wants, in the way you want, whatever you want to do. So yeah, that was it. And let's now move on to the next slide. So so here we can see that a scheduler. Yeah, here I'm telling about the scheduler. Scheduler is a program that manages the same definition I have repeat here again. So here we can see that after submitting our command group to the queue, the command group gets executed on the target device on the right device with the help of scheduler. Okay, and yeah, here we can see that the command groups instead of whether it is from CPU queue or GPU queue, both are going to the same scheduler, and then it will get the command group will get associated with the right device, CPU and the GPU. So that's the job of the scheduler, that this command groups will get executed on the right device. Now, here are some of the questions, some interesting questions. CPU or GPU, what would you prefer? Like for sum of elements in an array. So basically, if we perform, if we, so first of all, let me tell you that in CPU and GPU, they are in both of the device we can do, but and we can do some kind of parallel processing. The thing is that the number of threads that are available in the CPU are much smaller than the number of threads which are available in the GPU. Uh, like we have only few hundreds of threads in the CPU, and we have millions of threads in the GPU. Okay, but if you compare the individual speed, like if you compare the speed of one thread of CPU to one thread of GPU, then obviously this CPU thread is going to be much faster than a GPU thread. It's just that the GPU threads are much larger in number. That's why the offloading or whatever the computation that GPU performs is actually much faster, because the number of threads are on much larger side in GPU. But if you compare the thread individual, like if I take one thread of CPU and then one thread of GPU, then the CPU thread is going to be much faster. So when for sum of all elements in an array, what would you prefer? So here I won't say that you cannot perform sum in GPU. You can also do that, but there will be some synchronization that you will have to keep in mind, because let's suppose there are 1, 2, 3, 4, and 5. These 5 elements are in the array, and initially the sum int sum equal to 0. There is a sum variable which I have initialized to 0. So when I have to do sum, I will have to make sure that no two elements are performing the computation at the same time. Suppose this two value first reads the sum is initially 0, and then 5 also reads that the initial value is as 0. Then what will happen is that either 2 will update this or 5 will update this. So I won't get 2 plus 5 as 7. Either I will get 2 or I will get 5. So this will be the synchronization that will be there when we will do the sum using the GQ. So how we can overcome that, we will see in the future classes. But I would say that if we will perform a computation using CQ, it will be just you will have to write a sequential code. Okay, just you can write a for loop. But if you will perform it using GPU, obviously the results will be faster, but there will be some synchronization that you will have to keep in mind. And how will you do it? So I want you guys to think. So obviously for this, yeah, you will perform you should prefer GPU because it will compute that result much faster. Now, for finding whether a particular element exists in the array or not. Okay, for this computation also, we will prefer GPU. Why? Let's suppose there are n elements in the GPU. So you will launch n threads in parallel, and the element that you need to find. Okay, suppose I want to find 9 out of 100 elements that I have in the array. I want to see whether there is number 9 in the array or not. So what n threads will do? This n threads will compare each element to 9, and if any one of them finds 9, it will mark that boolean variable as true. That's it. So you will get that in a big O of 1. Just like if suppose in comparison to one element, it will take x time. Suppose it is taking x time, then the overall computation will take x time only because it is performing in parallel. But if you will do it in Sycl, what you will have to do is that you will have to compare it one by one. So suppose one comparison is taking one comparison is taking y amount of time. Then if there are n elements in the array, it will take overall n into y time. Okay, so for this also you will prefer GPU. Now for finding the maximum and minimum element in the array, for this uh, I would say that CPU that you will have to prefer. Why? Because let's suppose for maximum element, the initial maximum element is 0, and let's say there are elements in the array from 1 to 100. So it might happen that 5 and 10 both read maximum initially as 0. So either 5 will update it or 10 will update it. So let's suppose first 10 updates the maximum element, okay, as 0, from 0 to 10. But 5 has already read that initial value of maximum is 0. So what 5 will do, it will replace 10 with 5. So now there is some synchronization issue and we are getting the wrong result that we don't want. Okay, so for that we will have to use CPU because we have to just run in CPU. What we will do, just we will run a single loop because here for a maximum and minimum we will have to use atomic, and this and that atomic will make the things sequential on. If we do it in GPU. So think about it. Now coming on to the Sycl code structure. So we'll take a 5 minute break and 5 or 2 3 minutes of break, and then we will continue. Okay. Okay, let's begin. So we were seeing Sycl code structure. Okay. Sycl programs are basically standard C++ overall, and all in all, we can say. Then the program is basically invoked in the is invoked on the host computer, that is on the CPU, and yeah. So the program is invoked on the host computer and offloads computation to the accelerator, that is the device. So a programmer uses Sycl, queue, buffer, device, and kernel abstraction to direct which part of the computation and data should be offloaded. And as a first step in Sycl program, we create a queue, okay, and then we offload computation to a device by submitting tasks to that queue. Then the programmer can also choose CPU, GPU, FPGA, and other device through the selector. And this program uses the default queue here. Default queue, if you don't mention anything, which means that Sycl runtime will select the most capable device available at runtime by using the default selector. Okay. So now coming on to CPU versus GPU memory. So in computer system, device like a GPU and a host like CPU can either share the same memory or can have their own separate memory space. But when we are using Sycl, we don't really need to worry about managing the data transfer between the memories. Okay, between these memories, Sycl automatically take care of this for us, which means that we can work with data on the device and the host without having to manually copy the data back and forth between their memories. And Sycl automatically handles the data movement, which allows us to focus on our programming task without the added complexity of managing memory transfer. So here I've seen here you can see that uh, we can directly create buffer, okay, or we can create a buffer for an array or a vector. Sycl provides us the buffer class, which represent a buffer that can be used to transfer data between the host and the device. And we create buffers for various data types, including array, vector, and individual data items also, like int, float, double. So here are the common scenarios, like creating a buffer directly. Okay. So what this line is doing? Okay, what this line is doing is that it creates a buffer of integers with a one-dimensional range specified by the variable n. The buffer can be this buffer can be used to transfer and manage data of type int between the host and the device. Similarly, creating a buffer for an array. Like in this case, a buffer is created for the array. Okay, for the array that is named as my array, integer array. The data member function of the array provides a pointer to the underlying data, which is then used to create the buffer. And this allows us to work with the data in the array using the buffer in your Sycl code. And similarly, like above, we can create a buffer for vector or any other suitable data structure. So the creation of buffer for arrays and vectors enable us to leverage the Sycl framework for parallel processing and data transfer between the host and the device, facilitating efficient data management and parallel computation. Now, coming on to the now coming on to the dependency with X. One second. So here we go. Now, wait a second. So here I'm trying to show the implicit dependency with accesses. Now, let's suppose there are four kernels: kernel 1, kernel 2, kernel 3, and kernel 4. So, what this line is telling us that kernel 2 is depending on the kernel A. So, whatever the changes that the kernel A will make, those changes will require for will require those changes will be those changes must be reflected before we start the kernel 2 execution, because depending on what changes we have made over kernel 1, uh, we will change those in the kernel 2. So here A and B are representing that we have two arrays, A and B. So firstly, we are changing the values of array A in the kernel 1. Then whatever the changes that we have made in kernel 1, we will see that in the kernel 2, and accordingly we will change our we will change the values in the array A. Similarly, in kernel 3, we are manipulating the data in the array B, and then those updated values in the array A and B will be read by the kernel 4, and the kernel 4 will do the computation. Let's see the code. It's not responding. Wait a second. Yeah. So here is the program of the dependency graph. So here we have created a buffer of type int of range num, which is initialized to 60. So we can say that we have two buffer of int of size 60. Now there are four queues. The q1 dot submit, what it is doing, it is changing the values in the array A. We have made accessor for the buffer A, and in q2 we are again changing the values in the array A. Okay, so suppose initially in array A there are garbage value, but we don't need them. Okay, so we are here we are initializing the array A with values 0, 1, 2, 3, 4, whatever the index, because the index will go from 0 to 15. So the corresponding index values are stored in in these buffer A. And then in the q2 dot submit, what we are doing just 0 plus 0, then 1 plus 1. So the first will contain the zero index will contain 0, the first index will contain 1 plus 1, the second index will contain 2 plus 2, the third index will contain the 3 plus 3, and so on. Similarly, here buffer B is also we are initializing it as the index number. So 0, 1, 2, 3, 4, and so on. And whatever the changes that we have made till this Q3 will be used in Q4. So in Q4, we have made accessors for both buffer B and A. And using that, we are multiplying those two arrays, those two buffers, buffer A and B, and we are storing that result in the buffer B. Okay. So here I have made four different queues. So if there is no dependency between Q1 and Q2, then what could have happened is that both of them could have executed in parallel. But since there are dependency involved between them, because first this will update the buffer A, and then this will update the buffer A. So now, since there is dependency between them, they cannot execute in parallel. Okay. Similarly for Q4, because Q4 is using the buffer, again making the use of buffers, then therefore it will have to wait till all these three tasks finishes. Okay, when these three will execute completely, finish their execution, then only Q4 can start. So here, that is what wanted to tell you, that if if they are dependent, okay, if there is dependency between them, then they cannot run in parallel. But there is no dependency between this kernel 1 and kernel 3, so they can execute in parallel if we make separate queues for them. If we will make just one queue, then in that one queue, obviously there will be all will be sequential. So instead of this Q1, Q2, Q3, Q4, if I would have made just one queue and I would have write that Q1 dot submit, Q1 dot submit, Q1 dot submit, and Q1 dot submit, then it would be sequential. So firstly, this will compute, then this will compute, then this will compute, and so on. But if you make multiple queues, then they can all execute in parallel. And we are not worrying about the dependency, because the Sycl, when we make use of buffers and accesses, the Sycl will automatically uh, take care of the dependency. So it will get to know that there's dependency involved between them. So it will not run them in parallel, even if we make different queues. It will first compute kernel 1, then only it will compute the kernel 2. That's the beauty of it. Now coming on to the synchronization host accessor. Wait a second. Yeah. So the host accessor is an accessor which uses the host buffer access target. It is created outside of the scope of the command group, and the data that this gives access to will be available on the host. And these are used to synchronize the data back to the host by constructing the host accessor objects as buffer, because as buffer takes the ownership of the data. Uh, Creating a host accessor is a blocking call, and will only return after all the enqueued Sycl kernels that modify the same buffer in any queue completes execution, and the data is available to the host via this host accessor. Okay, so what is trying to say that here I have made a buffer. So the buffer takes the ownership of this vector. So whatever changes that I have done over here in this buffer using this accessor will not be reflected on these vectors, because the changes that I have made will be in the device, and will reflect only in this buffer. So if I what if I want to and this accessor I have made it for this device, because I have made it inside the queue, and this queue is associated with some device, and this H is written over here. Okay, so since this handler is associated with this queue, and this queue is associated with device, so this accessor will get to know for which device to which device it must be associated. Now, if I want to access the buffer values in the host, then what will I have to do? I will have to make another accessor known as host accessor. So this host accessor uh, will let us access the buffer values in the host part, because this buffer has already taken the ownership of this vector. So it's better to use this buffer, okay, instead of this vector, because if we will use the vector, then we will not get the updated value. Okay, even if you want to get the updated value of the vector over here, if you want that if I write v of I over here and you want to see the updated values, then what we will have to do, we will have to copy the buffer values to this vector. Then only you can save. But since there is no need of it to copy back and forth, you can just make an accessor for it and then get those desired results. Now synchronization, buffer destruction. So in the above example, buffer creation happens with a separate function scope. When execution advances beyond this function scope, buffer destructor is invoked, which relinquishes the ownership of data and copies back the data to the host memory. So in the above example, it doesn't mean this one. It means the here. Better I write below over here. So what it's trying to tell is that here I have made a vector and I've made a queue. Then I am calling a function dpcpp, dp++. Then I sent vector and the queue, their reference, and passed it as reference. So here again, for this vector, I've made a buffer. This R is taking care of the range of this vector, one dimension and the size n. Okay, so same is the same thing. Q dot submit accessor, and then we are performing some computation AI -2. We are reducing all the values inside this vector by 2. So what happens is that once this function gets over, okay, once we come out of this function that is back to here, uh, the buffer gets destroyed. And since we are not copying back it to the vector, we should not get the updated value accordingly. But it does not happen. Why? Because Sycl takes care of this thing. It gets to know that since the buffer is getting destroyed and the buffer data has been changed inside this s.parallel for, so what it will do before buffer gets destroyed, this buffer value gets copied back to this vector. So when you will come over here in the main function, when you will return to the main function, you will see the updated values using this vector v, because the buffer values before getting destroyed is getting copied to the v of I. So that is what it. So that is what this it is telling us. Okay. Now coming on to the matrix multiplication. So the one thing that we can do very efficiently using GPU is the matrix multiplication. Let's see how. So as we know that for matrix multiplication, one thing that we need is the if the first matrix is a P into Q and second matrix is R into S, then this Q and R must be same. Okay, then only this two matrix can be multiplied. Okay, so since we all know that in the matrix multiplication, we require 3 for loop. Why 3 for loop? Because first is for row and second one is for column, and the one is for performing this computation, that is ABC is getting multiplied with RUX. So one for this loop, one for moving in the array, one for moving in the column. Okay, so 3 matrix for matrix multiplication require 3 for loops. So if we write it in the CPU, what happens is that firstly we will compare this AR, BU, CX. Okay, then we will compute this value, and then we will compute this value. But since there are no dependency involved between these values, what we can do is in the GPU, what we can do is that we will perform all these 9 computation. That is 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we can perform this 9 computation individually or simultaneously, we can say. So let's suppose in computation time for this cell is to compute this AR, BU, and CX is X. Then all will be done in the same time. So the overall time is X only. But if it is taking Y time in CPU, then the overall computation of this matrix will be 9Y. Okay, so that's why if there is some large matrix, if we perform some large matrix multiplication, then the time required by GPU to perform those matrix multiplication is very small as compared to those of CPU. So this is homework for you guys. I want all of you to try this matrix multiplication code. Okay, just perform those computation in the GPU parallelly and note down the difference so that you will get to know how much fast computation can be performed in GPU. Okay, so make sure that you will have to use range 2 because this matrix is two-dimensional. Okay, so I will also share the code, but I need you guys to try this on your own. Okay, so that's all for today. And yeah, thank you.